In our previous module, we saw about SN2 reaction and we observed that the rate of the reaction depends on both the concentration of the alkyl halide and the concentration of the nucleophile. So for SN2 reaction, we can write that the rate equals rate constant into concentration of the alkyl halide and the concentration of the nucleophile. Now, given our understanding of the SN2 reaction, let's consider what would happen if a tertiary halide would react with a very weak nucleophile. So this is the structure of a tertiary halide, which is 2-bromo 2-methyl propane, and let's say it reacts with water, which is considered as a very weak nucleophile, and we end up getting 2-methyl 2-propanol. Now, given our understanding, we expect that the rate of this reaction, because it's a tertiary halide, it's a tertiary alkyl halide, and this is a very poor nucleophile, we would expect that the reaction would be very slow, because from the understanding of SN2 reaction, we observe that this alkyl halide, a tertiary alkyl halide, is sterically hindered to be attacked by the nucleophile. And also because this nucleophile here, water, is a very poor nucleophile, and we expect that the reaction would be extremely slow. But it turns out that the reaction is actually very fast. So compared to an alkyl halide which is unhindered, like a primary or a methyl alkyl halide, this reaction is about 1 point or about 1 million faster. That is 12 lakh times faster than a unhindered primary or a methyl bromide. So this tells you that the reaction actually undergoes via a completely different mechanism, and this mechanism is called as an SN1 mechanism, which means the rate depends only on one of the reactant, and it turns out that the rate equals K into the concentration of the alkyl halide alone. That means only the alkyl halide is involved in the transition state, or that becomes the rate determining step. Here in the SN1 reaction, the S, as we know for it from the previous case, it stands for substitution. The N stands for nucleophilic, and 1 stands for unimolecular. That means in the rate determining step, only one molecule is involved. Now let's look at the mechanism for the SN1 reaction of an alkyl halide. Now the first step of the reaction is, so let's me write the tertiary halide, which is the 2-methyl 2-bromopropane. So the first step of the reaction is that the carbon halogen bond breaks. So this bond breaks. So let me just draw this. So, and when it breaks, the halogen takes with it the bonded pair of electrons. And this is a very slow step. This is a very slow step. And what this gives you is a tertiary carbocation. And the halide leaves as Br minus. Now, if you look at this carbocation, you will realize that it's a tertiary carbocation. And we have studied that tertiary carbocations are very stable. So that is the reason why this reaction is much faster than what we would have expected if it had followed an SN2 mechanism. In the second step, the nucleophile, which is in this case water, rapidly attacks the carbocation. So it rapidly attacks the carbocation, which is, so this tertiary carbocation actually acts as an electrophile. That means it has behaving like an electron loving species because it is positively charged. This gives rise to a protonated alcohol. This gives rise to a protonated alcohol. So let me just write that structure for you. So this gives rise to a protonated alcohol with a positive charge on the oxygen. And this protonated alcohol then in the next step rapidly loses a proton to water. So this protonated alcohol rapidly loses a proton to water. So let me rewrite the structure. So let me write this in an expanded form. So this will leave as a, this hydrogen will leave as a proton, and a water molecule abstracts this proton, giving rise to a tertiary alcohol. So if you look at the mechanism of the reaction, we saw that in the first step, the carbon halogen bond breaks. The carbon halogen bond breaks and the leaving halogen takes the bonded pair of electrons with it. And this step is the slowest. This step is the, and this step is the slowest step, or so we call it as the rate determining step. In the second step, the nucleophile rapidly reacts with the carbocation, which actually acts as an electrophile to form a protonated alcohol. This protonated alcohol then uses a proton to give a tertiary alcohol, which is your final product. Evidence which we observe is that the rate of this reaction is about 1,20,000 times faster. No, it's about 1 million times faster. So it's not 1,20,000. It's like 12 lakh times faster um, than what you would have observed, the rate you would have observed if it had followed an SN2 mechanism for a primary or a methyl halide. And based on the mechanism, we can see that because carbocations are formed easily in case of a tertiary alkyl halide. So if the tertiary alkyl halide is involved, it will be more reactive because a carbocation is formed easily if it is a tertiary carbocation, and this tertiary carbocation is a extremely good nucleophile, and hence the attack by nucleophile is also a much weaker, right? So that also justifies the observed rate for this reaction. And the third is that in an SN2 mechanism, we said that there is all what we call as an Walden inversion, which means if we start with an substrate which is in our configuration, the product would turn out to be an S configuration. That is, there is inversion of chirality, which is the very characteristic feature of an SN2 reaction. This we have observed for SN2. But over here, since a carbocation is involved, and we also know that in carbocation, the carbon is sp2 hybridized, is sp2. So this is the carbocation, and this carbocation is actually sp2 hybridized. So this carbocation is sp2, the carbon bearing the positive charge, that is sp2 hybridized. And if it is sp2 hybridized, then it is a planar molecule, or we can say that, so here you have one methyl group, you have another methyl group projecting outward towards, that is projecting towards you, and one methyl group which is projecting to the back of this paper. So the incoming nucleophile, which in this case is water, can attack either from this side or can attack either from this side. And if this nucleophile attacks from the opposite side, okay, if it attacks from the opposite side, of the departing relative to the departing alkyl halide. So if your alkyl halide is leaving in this direction and the nucleophile is attacking at the opposite side, you will have the inversion of configuration. But if the nucleophile attacks on the same side as the departing halogen, then you will have a retention of configuration. Now, this is the biggest justification or the proof that a carbocation is involved.